Hi everyone, welcome to part 4 of our lectures on chapter 6. Today we're going to talk about thermochemistry, especially as it applies to the enthalpy of a reaction, and then we're going to use our enthalpy of a reaction to use Hess's law. So first we're going to continue talking about our enthalpy of the reaction, and last time we talked about the fact that the enthalpy of the reaction can be used stoichiometrically, right? Which means that for every 1 mole of carbon, we're getting out negative 393.5 kilojoules. And remember that since delta H is negative here, this is telling us that this is an exothermic reaction. But say we were to multiply our reaction by a number, right? And so here we've multiplied this reaction now by 2. So we've got 2's in the front of all of them. This would cause our delta H value to be doubled, right? So we're going to also multiply it by 2. And the reason that we can do this is because delta H of the reaction, our enthalpy of the reaction, is extensive, which means that it depends on how much stuff you have. So if we double our reaction, then we're going to double the amount of heat produced. And I think this makes sense from a logical standpoint. If we reverse the reaction, then we will change the sign of delta H. So for example, if instead, right, normally we have carbon and oxygen, we're reacting them together to get carbon dioxide. This is an exothermic reaction. We're going to produce negative 393.5 kilojoules. But if instead I wanted the reaction to go the other way, I wanted to, decompose my carbon dioxide and break it back apart into carbon and oxygen. So that would be this reaction here. We're decomposing carbon dioxide, breaking it back into its elements. That would mean we are going to flip the sign of the reaction. So instead of getting out negative 393.5 kilojoules, we needed to put in 393.5 kilojoules to decompose the reaction. So now instead of it being an exothermic process, it's an endothermic process. So on this slide, if we multiply our reaction by a number, then we're going to multiply our delta H by that same number. So in that case, it's doubled, so we're going to double our delta H. If we reverse the reaction, then we are going to flip the sign. So instead of it being negative, now it will be positive. And the reason that I'm talking about all of these delta H's is because we are going to use them in our Hess's law calculations. Hess's law states that the change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. So in this reaction, over here, okay, we have, 2 different reactions that are happening. We have reaction 1, which is where A plus 2B is going to make C, and then we have reaction 2, where our C is going to decompose into 2D. And so the reason that we're talking about this is normally reactions don't just happen. It's not just like A plus B makes C, the end. Usually there's a bunch of little reactions that happen along the way, like these 2 things make this thing, and then that thing decomposes to make this thing, and then that reacts with something else to make this thing, right? And so there's this series of reactions. Normally, though, when we write a reaction, we're just writing the overall reaction. We're not writing all of these little individual reactions that are happening along the way. But most reactions are actually stepwise. So what this is saying is that each one of these little reactions that happen, right, these 2 delta H's that are happening for these little reactions, we can add them together to get the delta H for the overall reaction, which would be this arrow here. So like if we add, right, if we were thinking about vectors, if we add, this blue arrow plus this red arrow, we would get this purple arrow here. Okay, so we can add up all of the little reactions, all of those delta H values for the little reactions, and we will get the delta H for the overall reaction. Okay, and this will actually make more sense as we go through an example. So like here, this is an example. Calculate the change in enthalpy for the combustion of methane. And so this is a combustion reaction, which tells us that we're reacting a hydrocarbon with oxygen gas to produce carbon dioxide and water, and of course you're going to balance it, all of that good stuff. So we have all of our delta H values for the individual reactions that are going to happen along the way. Carbon is going to react with hydrogen to make methane. We have carbon and oxygen to get carbon dioxide. We have hydrogen and 1/2 oxygen to make water. These are all actually formation reactions, which we're going to talk about a little bit later. But for now, I want you to think about them as kind of individual stepwise reactions that needed to happen in this overall reaction. Okay, and each one will have a delta H value. For problems like this, you are not going to be expected to write well, you'll sometimes be expected to write these. These are formation reactions. And again, I'll show you how to write those later. But you will not be able to memorize any delta H values. I will always give them to you. Okay, so I may ask you to write the formation reactions, but I won't ask you to memorize delta H values. What I will ask you to do is I will ask you to manipulate these reactions so that they equal the overall reaction. And so this is how it goes. If we look at this first reaction here, right, this one, do you see that methane is on the wrong side? In the first reaction, we had, right, our overall reaction, we have methane is in the reactants. But here in this first reaction, we have methane in the products. That's not what we want, right? We're trying to make it match that first reaction. So, right now methane is in the products of this first reaction, so we're actually going to flip it. And when we flip that reaction, we are going to flip the sign on our delta H value. So instead of it being negative, it's being positive. And I'm going to write, all of the, everything I do to the reactions down here. So I've flipped that first reaction. So now the methane is on the reactant side, just like it is in this overall reaction. And when I flipped the reaction, I flipped the sign. So now let's look at this second one. We look here and we see that carbon dioxide is on the product side, which it's on the product side up here, which is great. And so now we can just leave that reaction alone because carbon dioxide is already where we want it. So we'll just copy that below. Okay, so now let's look at the last one. The last one here, right, we have water on the product side, which is great. But up here in our overall reaction, do you see that there's a 2 in front of water? So we actually need 2 of this third reaction. So we're going to multiply all of the coefficients by 2. So a 2 will end up here. This 1/2 will go away because 2 times 1/2 is 1. And a 2 will end up there. And remember, when we multiply this reaction by 2, we're also going to multiply our delta H value by 2. Okay, so that will all get multiplied by 2. And again, the reason that we're doing all this is because we're trying to make our individual reactions cancel out and match this overall reaction. So we'll go ahead and multiply that one by 2. There it goes. And now we'll start to see, do our other things, right, the stuff that we're not looking at, the stuff that doesn't show up in this overall reaction, do they cancel out? These things are called intermediates. Like, do you see that there is no carbon in this overall reaction? There's no free carbon sitting around, but there's a carbon here and there's a carbon here. Well, the fact that the carbon is created and then used up in a later reaction, that makes it called an intermediate. It's something that's being produced during the reactions, but used up before the final product. So it's an intermediate. The same thing with our hydrogen, right? Our hydrogen is being produced, and then later it's going to be used up. So hydrogen is also an intermediate. So we want to make sure that all of these intermediates cancel out because they don't show up in our overall reaction. So we'll go through and make sure that's happening. Okay? So when we look at this, our carbons cancel out because there's one carbon on the reactant side over here, and there's one carbon on the product side up here. So they cancel. You can think about them canceling kind of like we would cancel out x's or something like that in an algebraic equation. So our carbons cancel out because they are on opposite sides of the arrow. And then our hydrogens will also cancel out. You need to make sure that the coefficient cancels too. Like there's 2 hydrogens here and there's 2 hydrogens here. And we would need them to have 2 on each side in order to cancel out correctly. And now if we look, we are only left with methane, oxygen, carbon dioxide, and water, which are what shows up in this reaction up here. So that's great. So we're going to add our reactions straight down, which means that we're going to get methane and then 2 oxygens because there's 1 here and 1 here. So, 1 plus 1 gives us 2. And then we have a carbon dioxide and 2 waters. So all of the stuff on the reactant side will end up over here, and all of the stuff on the product side will end up over there. It doesn't matter the order that you write them in. I've just written them in the same order than they show up in the overall reaction that we were given, but you could write them in a different order just as long as they end up on the correct sides of the arrow. And then our delta H values, we're simply going to add them all straight down. So we're going to add that 74.80 plus our negative 393.50 plus our negative 571.66, and we add those all together, we will get negative 890.36 kilojoules. And so that would be our delta H value for this reaction. okay? So Hess's law, we need to be able to manipulate these equations in order to equal our overall equation. Let's try another one. This says, given the following information, calculate delta H for the reaction below. So these are our two sub-reactions here, and then we need to figure out what would be our delta H value when we manipulate them, we add it all together for this overall reaction down here. If you'd like to, go ahead and pause here and try to do the problem yourself. Once you've tried it out and you're ready to see the answer, come back and I will show you. Okay, let's go over the answer. So here is all the information from the previous slide. So we have, our first reaction, our second reaction. We're going to need to manipulate them so that we can figure out our overall reaction. So in looking at this, do you see that we have chlorines in both of these, right? Chlorines are there, but they're not in our overall reaction. This is telling us that our chlorines are intermediates, and at some point they're going to need to cancel out before the end. Everything else, right, shows up in the overall reaction. We have copper 2 chloride and copper 1 chloride. And so we can't base our work off of copper, right? So here's copper here. And we actually can't base what we're going to do off of copper because, as you can see, copper shows up in both of these two reactions. So that's not really helping us figure out what to do. We need to figure out what to do based on substances that only show up in one of the reactions. That will make our lives much easier. So let's look at copper 2 chloride here. If we look at copper 2 chloride is on the wrong side. We have the right number of copper 2 chlorides, right? We have one of them, and that's what we needed in our overall reaction here, but it's on the wrong side. It's on the product side, and we need it to be on the reactant side. So that's telling us that we need to flip this first reaction so that our copper 2 chloride ends up on the reactant side. So there we go, we flipped it. And when we flip it, we need to also flip the sign. So that negative is going to become a positive. So now if we look at the second reaction, we have 2 copper 1 chlorides on the reactant or on the product side, and in our overall reaction, we have 2 copper 1 chlorides on the product side. So that's telling me we actually don't need to do anything to our copper 1 chloride because it's already on the right side. We have the right amount of it, so we can just copy it down below. Okay. Now our last step is to add them together and make sure everything cancels out. So when we do that, our copper will cancel with one of the coppers from below. Okay, so you can think about it, if we had like an X and then a 2X, essentially, one of the X's would cancel out. So we have 1 copper on the right, in our products, and we have 2 coppers on the left, which means we're going to end up overall with just 1 copper on the left, 1 copper on our reactant side. And then our chlorines will go ahead and cancel out because there's 1 chlorine on each side of the arrow, 1 chlorine on the products, 1 chlorine on the reactants. And then looking at this, when we copy it down, we have 1 copper, and then we have 1 copper 2 chloride and 2 copper 1 chlorides. And so we'll copy all of that straight down, and that matches this overall reaction that we were trying to find. So now we can go ahead and add together our delta H values, and we will get our delta H of the reaction. Here's another one. So go ahead and pause here. I think you've got a general idea of how to do this now. Pause here and try to do this one. It's a little bit trickier, but I think you can handle it. Once you're done, go ahead and unpause and come back and see the answer. Okay, let's go over it. So here's all the information from the previous slide. We have 3 sub-reactions, and we need to figure out how to cancel them out in order to get that overall reaction. So again, we're going to look at things that just show up in one place. We have some intermediate oxygens, right? We have oxygen showing up in every single reaction, but there's no oxygen in our overall reaction. So that will need to cancel out along the way. Similarly, we have nitrogen in 2 of our reactions, but we don't have any nitrogen in our overall reaction. So those will need to cancel out along the way. So we can't base what we're doing on oxygen because those will all get canceled out. We can't base what we're doing on nitrogen because those will all get canceled out. But we can base what we're doing and we also can't base what we're doing on nitrogen monoxide because, as you can see, it's showing up in 2 different places, right? in one reaction, it's showing up in the reactants. In one reaction, it's showing up in the products. And we want to use things that are just showing up in one place. So we can look at nitrogen dioxide to tell us what to do. We can look at our water, and we can look at our nitric acid. So we're going to look first at this reaction, okay, this first one. If we look at our first reaction, nitrogen dioxide is on the wrong side. Right here, it's on the product side, and we want it to be on the reactant side. And we also, do you see that there's a 2 here? And we want it to be a 3. So first step, we're going to flip it, right? We need to flip it so that the nitrogen dioxide ends up on the reactant side instead of on the product side. What's a little bit trickier is that we need to change that 2 into a 3. And the way that we do that, right, we'll multiply that 2 by 3 halves. And when we multiply it by 3 halves, those 2's cancel out, and we're left with a 3 as the coefficient. And this is the only reason that this is trickier is because people generally don't like fractions. So this particular problem is full of fractions, and I'm sorry, but that's just how life happens sometimes. So we're going to flip this whole reaction, which means we flipped the sign, right? So we're going to multiply it by a negative, and we're going to multiply all of our coefficients by 3 halves. And when we multiply that by 3 halves, that's going to change this into a 3. That's going to change this into a 3. And then we're going to end up with 3 halves O2. Or you can write, 1.5 if fractions aren't your friend. But it tends to be a little bit easier, actually, to leave them as fractions when we're doing these Hess's law type problems. Okay, so we've flipped the first reaction, and we've multiplied it by 3 halves. Now let's go ahead and look at the next reaction. So here, right, we're going to base this one. You can look at nitric acid or you can look at water, but either way we have twice as many as we really need, right? Here we only have 1 water and we have 2 nitric acid, and in this one we have 2 waters and we have 4 nitric acids. So we're going to multiply this whole reaction by 1/2. And when you do that, I would think of it as multiplying by 1/2 instead of dividing by 2. I know it's the same thing, but it tends to be a little bit easier to think about it as multiplying by 1/2. And again, I would leave them all as fractions for now until you get to the overall reaction. We're not going to flip it or anything. We're just going to multiply by 1/2. And when we do that, we're also going to multiply our delta H by 1/2. So when we multiply this by 1/2, we're going to get 1 N2. We're going to get 5 halves O2. We're going to end up with 1 water and 2 nitric acids. Okay. Now we're going to look at the last one. And the last one, right, we're going to base this one on nitrogen monoxide. Okay, and the way that we're going to do this, do you see that we already have 3 nitrogen monoxides up here? Well, in our overall reaction, we only want to have 1 nitrogen monoxide on that side. So we're actually going to use this last reaction to get rid of the extra nitrogen monoxides. Okay, so we have 3 nitrogen monoxides here. So if we have 2 on the reactant side, right, then 2 of them from this 3 will cancel out, and we'll only be left with 1 on the product side. This reaction is also being used to cancel out our nitrogen and our oxygen. If you look, right, we talked about nitrogen and oxygen are our intermediates. Right now we have 1 nitrogen that's still going to be left on this reactant side. So we're going to make sure that there's 1 nitrogen on our product side in this reaction so that they will cancel out and they will be gone. Right now we have 5 halves oxygen on our reactant side, and we have 3 halves oxygen on our product side. So we need another, essentially 2 halves, right? Or just 1, but, if we think about this as 2 halves, like I said, think about it in fractions. If we think about another 2 halves oxygen on the reactant side, then we'll have total 5 halves on the, on the product side. We'll have total 5 halves on the product side and 5 halves on the reactant side, and they will cancel out. So, in summary, this last reaction is used to get the right number of nitrogen monoxides and to get all of our intermediates to cancel out. So as you can see, this problem is a little bit trickier. So when we flip this reaction, we've flipped the sign and we have negative 183 kilojoules. Now we can go through and look at this messy equation and make sure that everything cancels out. Okay, so our nitrogen monoxides, like I said, those are going to be reduced. And so, the 2 of them will cancel out 2 of these so that we're just left with 1 nitrogen monoxide because we had 3 before. Then we're also going to make sure that all of our oxygens cancel out. So total on the reactant side, we had 5 halves oxygen. And total on the product side, we had 3 halves plus, like I said, 2 halves oxygen. So those are going to cancel out. And then we make sure that our nitrogens cancel out as well. So we have nitrogens canceling on both sides. So this nitrogen canceled with this nitrogen. And I know this is looking a little messy. It's going to get much clearer in just a second because we're going to add it together. So left over, we have 3 nitrogen dioxides. We have 1 water. We have 2 nitric acids. And we have 1 nitrogen monoxide. So that's what's left out of all of this. And again, we double check, we make sure that's actually what we were trying to get. Now you can go ahead and add together all of those delta H values, and you'll get your delta H of the reaction. Okay, so these reactions sometimes are a little bit tricky. People tend to struggle the most when they have these fractions. So make sure you're getting a lot of practice. There are a lot of practice problems in your Chapter 6 lecture worksheet. So before, I was alluding to the fact that we were writing formation reactions, and I said we'd get back to those a little later. So this is later. So first, before we can write our formation reactions, we need to talk about standard conditions. And the standard state is the state of a material at a defined set of conditions. And so it's the state of the material at, of a gas at 1 atm, or a pure solid or liquid at its most stable form at 1 atm of pressure. Okay, so all of this is at 1 atmosphere. Usually we're going to look at these substances at 25 degrees Celsius because this would be room temperature. So essentially, what this all boils down to is what state is this material if we were working at it in lab, right? Our pressure in the lab is about 1 atm, and our temperature in the lab is about 25 degrees Celsius. It's usually a little cooler. And so that's when it asks about the standard state, it's literally just asking what state is the material like in the lab. If you look at a periodic table that has colors, the one in our lecture room actually has anything that would exist as a solid state, that chemical symbol would be written in black. Anything that exists as a gas at room temperature has that chemical symbol written in red, and the 2 that exist as liquids, mercury and bromine, will be written as blue. Okay, and so that would be helpful if you're looking for elements, but sometimes we'll need other things like compounds and things like that. So we can write a standard enthalpy change is when we write all of these reactants and products in their standard states. Okay, and so if you're seeing this delta H naught, that just tells you that everything is in its standard state. Okay, and then we can also write, which is what we're going to focus on more in this class, the standard enthalpy of formation. So writing these formation reactions is when we're going to write 1 mole of a compound, and I want to emphasize we are making 1 mole of a pure compound from its elements. And so we're going to write all of the elements in the standard state. And so, if you have carbon, you're going to write it as a solid. If you have oxygen, you'll write that it's a gas, things like that. And then we're going to write these formation reactions, and we can use them as a part of Hess's law. Once we get to it, so we'll have different values for our delta H's of formation, and we can calculate delta H's of formation for compounds. But the delta H of formation for a pure element in its standard state is always going to be 0. So like the delta H of formation for, let's say, hydrogen gas, that's going to be 0 kilojoules per mole because it is a pure element in its standard state. And it doesn't matter, right, the fact that this, the hydrogen is diatomic. We know our diatomic elements. We are going to remember Hofbrinkel or however you've chosen to remember them. So all of those elements, when they are in their standard state, they will exist as diatomics. Any other elements, like say carbon, carbon will exist by itself as a solid, and it will still be 0 kilojoules per mole because it's a pure element in its standard state. So these guys, though, will exist as diatomics in their pure element standard state form. Okay, so we can calculate our delta H of formation for compounds, but if we are ever asked for the delta H of formation for a pure element in its standard state, that's going to be 0. So here you go. We can look at this. Like I said, bromine is a pure element in its standard state as a liquid, so that's why its delta H of formation is 0. We've got a metal here. This is calcium. Calcium is 0 in its standard state as a solid, but as you can see, like the compounds, right, they are not 0. They have a, an enthalpy of formation, and we can calculate that, from the different reactions that happen to form it. Here's carbon in its standard state, right? We have chlorine gas in its standard state. And you'll notice this is a diatomic chlorine. Monatomic chlorine is not in its standard state, so it has a delta H formation. And then we've got fluorine, right? It's diatomic, nitrogen, all of that good stuff. We've got silver up here. Silver would be a solid. Sodium would be a solid. So these are different elements in their standard states, and you can see all of the compounds, or when the elements are not in their standard states, like sodium gas, right? If you wanted to make it a gas, right, it would have a delta H of formation. We need to input some energy to make it be a gas. So like I said, if you see an element in its standard state, the delta H of formation is always going to be 0. If you see a compound or an element not in its standard state, then you might be asked to calculate the delta H of formation, or it would be given to you. All right, so we can write formation reactions where we're taking these elements in their standard states to form 1 mole of a pure compound. And if you're not sure what the standard state of an element is, you can find Appendix 2B and figure out where it has delta H of formation is equal to 0. So like looking at this, this is not what I'm referring to, but looking at this, if you weren't sure what state sodium should be, whether it should be a solid or a gas, you can look and see which one is 0. That's telling you that sodium is its standard state is a solid. Okay, and then when we're writing these formation reactions, we're always going to make it form 1 mole of our compound, 1 mole of our product. And since we're trying to make it form 1 mole of our product, sometimes the coefficients of the reactants might be fractions, okay? This is something that we're generally unfamiliar with because we've been told, all of your, coefficients need to be whole numbers because you're not going to write, you're not going to react half of a mole of carbon with something. But when we are writing formation reactions, we are going to write the coefficients as fractions if we need to, because we are always going to form 1 mole of our compound. So let's go ahead and see what this looks like. So if we have carbon dioxide, and we're trying to form it, we will form it from carbon and oxygen. Okay, so we're trying to form 1 mole of carbon dioxide. So going backwards, we need carbon in its standard state. Carbon would be a solid, and oxygen would be a gas. Okay, and so carbon plus oxygen will give us carbon dioxide. And in here, we don't need any coefficients because, we already have 1 mole of this. We needed one carbon, and carbon in its standard state doesn't have a subscript. We needed 2 oxygens, and oxygen's diatomic, so we're all good to go there. Let's try another one, a little bit trickier. C6H12O6. So this is sugar, right? This is going to be a solid, and so we need to figure out how we would form sugar from its elements. So again, we're going to have carbon and oxygen like we did before, but we're also going to have hydrogen, which is also diatomic. So it'll be carbon plus hydrogen plus oxygen. So here we needed 6 carbons to get our C6. We needed 6 diatomic hydrogens to get H12. And we need 3 diatomic oxygens to get O6. And if we, add those all up, we make sure that we've got the right amount. We get C6H12O6. So again, we're writing all of these elements in their standard state. So carbon's a solid, hydrogen's a gas, oxygen's a gas. Okay, let's try another one. This is ammonia. So ammonia is going to be formed from nitrogen and hydrogen. But when we think about this, right, we have nitrogen is diatomic and hydrogen is diatomic. Okay, I only need 1 of these nitrogens, right? So I'm actually going to end up multiplying this by 1/2 so that I only get 1 of those nitrogens. And when we need, right now I have 2, but I need 3 hydrogens. So we're going to multiply this by 3/2 so that I end up with 3 hydrogens. Okay, so again, I know this is a little bit weird to have these fractions here, but we need to have the fractions in order to make only 1 mole of ammonia. If this is making you kind of uncomfortable and you're like, a little bit confused, what I would do first is write out, okay, nitrogen plus and then nitrogen's a gas, and then hydrogen is a gas, and it's going to make ammonia, which is, and it's a gas, and go through and balance it first. That might make it a little bit easier, right? So we would put a 2 here, and we would put a 3 there. And then, go through and make sure you only need 1 of ammonia. So what I'm going to do is multiply everything by 1/2 so that I only get 1 ammonia. So then it would be 1/2 into gas plus 3/2 H2 gas gives us just 1 ammonia. So if you don't like the way that I was talking about doing it before, write out the balanced reaction and then figure out how to get that coefficient in front of your product as just 1. Because we only need to make 1 of each one of these. So every time we're writing formation reaction, you're only forming 1 mole of your products. So we can use these formation reactions in Hess's law. We can also use, because all of these formation reactions, we're forming these different compounds, and we have values for these formation reactions, essentially. So if we go back and we look all the way back a couple slides here, right, we have these values for how they're being formed. We have the delta H of formation for a bunch of different compounds. And we can use these delta H's of formation in Hess's law. So if instead we weren't given all of these individual subreactions, if instead we were given delta H's of formation, we can use those in a very similar way. The reason, right, we don't need all of the individual reactions is because the formation reactions are kind of implied, right? If I'm given a delta H value for the formation of carbon dioxide, we know this is what happened to form carbon dioxide. And so instead we can just use, okay, I have a delta H of formation value for carbon dioxide, and we can use this a little bit differently. And the way that we're going to use this is we're going to say, okay, our delta H of our reaction is going to equal the sum, right? So that's the Greek letter sigma. That's going to say the sum of the delta H values of our products multiplied by their coefficients minus the sum of the delta H values of our reactants times their coefficients. Okay, this is a little bit easier. It's just going to be dependent upon what you're given. If you're given a bunch of subreactions, then you're going to manipulate them to find the delta H value. If instead you're given the delta H's of formation, you're kind of have those subreactions being implied, and you're just being given the delta H value overall, essentially. And we can use this delta H value to do products minus reactants. Okay, it's always going to be products minus reactants. That's what I want you to remember. So let's see how this can work out. Because we can write any reaction as a sum of the formation reactions or as the reverse of the formation reactions for the reactants and the products. All of our, if we have the products, those are being written essentially as the forward reactions, which is why they're being positive. If we have the reactants, essentially we've written the formation reaction backwards, if you can kind of think about it that way, because we are breaking it apart along the way, which is why this is going to be negative. So we're going to have, the delta H value of the products minus the delta H values of the reactants. And this will make more sense as we go through it. So let's try one. This is the same reaction that we were doing earlier, but we have different pieces of information now. Before, we had all of the formation reactions, which I mentioned, and we were given the delta H values that went along with them. And then we multiplied or, flipped or whatever we needed to do, all of those subreactions so that the delta H of the reaction could be calculated, right? We needed everything to cancel out so we could calculate delta H of the reaction from the subreactions. Well, instead, this time, I didn't give you all of those subreactions. Instead, I gave you the delta H of formation. Okay, so this is the energy that it took to make methane, to make carbon dioxide, and to make water. You'll notice that oxygen has a value of 0 because here this is, and I know I don't have the states up here, this is a gas. So oxygen as a gas is always going to be 0 because it doesn't need to be formed. It's going to have delta H value of 0 in its standard state. So the way that we're going to do this is we're going to do the products minus reactants. So we have, and actually I'll write above this, so we have our delta H value of our reaction. We're going to do our products. So we have carbon dioxide plus 2 times our value for water, right? Because those are our products. We're going to add those all together. And then we're going to subtract all of the values for our reactants. So we're going to have methane plus 2 times oxygen. Okay, so our value for carbon dioxide is 393.50, and then we're going to add together 2 times the value for water, and then we're going to subtract our value for methane, and this would be plus 2 times 0 for oxygen. But I've left that out because it doesn't matter. So we're doing products minus reactants. And then we can go through and add them all together to get our delta H value of the reaction. And if you go back and look at the previous slide, or the slide that we did this before, this is the exact same value, okay? And that's what Hess's law is. It tells you it doesn't matter how you got there. It doesn't matter if you got there by a series of subreactions or if they just reacted together this way. It doesn't matter how you got there. You can calculate the delta H for the reaction regardless. So in this case, we're using the delta H's of formation when we do products minus reactants. And in the other way, we had a series of subreactions that we needed to flip. It's just going to be based on what you were given. If you're given delta H's of formation, you'll do it this way. If you're given subreactions, you'll do it the other way. Let's try another one. This says calculate the enthalpy change of the reaction using the standard enthalpies of formation. So here we have a reaction. And we have our enthalpies of formation. You'll notice they did not give us a value for O2 gas. And again, that's because oxygen in a gas is in its standard state. So this is going to be 0 kilojoules per mole. So they haven't written it down because it's just redundant. So when we do this problem, we're always going to do our products minus reactants. So we will do, and I'll write this again above it, our delta H of our reaction is going to be 4 times our value for carbon dioxide, plus 2 times our value for water, and this is liquid water, and then we're going to subtract our reactants. So 2 times C2H2 plus 5 times our O2. Okay, so we have 4 times our value for carbon dioxide, 2 times our value for water, and then we're going to subtract our reactants, right? And I don't have that 5O2 because that's times 0, so that's redundant. And so then we can just calculate it all together and get our value. So nothing too tricky here. The only thing you'll need to watch out for is to make sure that you have correctly balanced your equation if it wasn't balanced to start with. And then make sure you're multiplying by the coefficients for all of these values. And then always do products minus reactants. And that's the end of this set of slides. So today we covered the delta H of the reaction. We talked about Hess's law a lot and how to do Hess's law 2 different ways. When you're given subreactions, which you need to flip and manipulate, or when you're given delta H's of formation, right? That enthalpy of formation. We also talked about how to write reactions for compounds from elements in their standard states. And remember, you're always going to form 1 mole of your compound. So that's it for Chapter 6. So go ahead, find your Chapter 6 lecture worksheet, do lots of practice problems, and get really good at this stuff, especially that form of Hess's law when we're needing to flip them, and there are fractions. That tends to trip people up the most. Get lots of practice, work on this a lot. Send me any questions you have, and I'll see you next time when we start Chapter 7.